let me ask you the same question. We're all made up of atoms and molecules. So atoms and molecules, are they also particles?
Yeah.
All right. I mean, you would think so, right? Because that's the way we look at things in modern physics.
I wonder if we
And
could.
so when you do the same experiment, the double slit experiment, by using electrons, for example, and this experiment was first carried out in 1924, 25, or 26.
And here we are, the
This is what they discovered.
granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange netherworld of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Weird. This is called quantum weirdness. The entire modern physics is based upon this. And this gave us the Copenhagen interpretation of quantum theory came out of this. And the results of the Copenhagen interpretation, you got the electronics technology that came out of it. You got the nuclear physics, the modern physics, quantum theory, the nuclear bombs, and all that, all sorts of stuff. Okay, so simply put, the particles that make up reality, if you're not looking, they will act like waves. So the question is, waves of what? And then the act of observation forces them to become particles in essence. So if you're not looking waves, if you're looking particles. So the question becomes, whose observation is responsible for creating the universe, forcing these waves to become particles that make up the universe in essence. All right, physics is really, modern physics is really, really weird. All right, so let's talk about light. nature of light. So far, it looks like the light is composed of waves, right? So when we have sunglasses, aside from the fact that you're going to look extra cool with sunglasses, the purpose of sunglasses is to reduce glare. So what is glare and how do you reduce it? Well, the sunglasses are made in such a way that they're made to reduce glare because they're polarizers. So let's talk about what polarization is. Polarization is it's related to the preferred axis of vibration. All right, so when you're polarizing something, you're selecting a preferred axis of vibration. All right, so this vibration, up and down vibration, is vertically polarized, and this one is horizontally polarized. So you can pick and choose the axis of vibration using polarizers in essence. So you can pick vibrations in this direction. So this would be vertically polarized, or you can pick vibrations on the horizontal direction. That would be horizontally polarized. And how do you pick and choose the vibrations the direction of the vibration? You do so by using polarizers. So notice that this one is a polarizer. So this is a vertical polarizer. So it's going to be able to allow passage for a vertically polarized wave. And then the horizontally polarized one is not going to be able to go through. It allows passage for it to go through. Here's unpolarized light. This is the sort of light that you get from the sun, from the light bulbs. All right. So what you are looking at is the random vibrations of the electric field component of the electromagnetic wave. By using a polarizer, you can pick and choose. All right, so here's the unpolarized light, and this becomes polarized going through a polarizer, in essence. All right, so your polarizer, this could be a vertical polarizer, or it could be a horizontal polarizer. If it's a vertical polarizer, only the vertical component is going to go through. I noticed that the intensity of light goes down by half. So yeah, I mean, the sunlight is going to get darker, so there's no question about it. All right. But at the same time, you get to pick and choose the angle of vibration. Yeah, you get to choose the direction of vibration that you want. So you get to polarize the light. All right, so you got a vertical polarizer, you got a horizontal polarizer. For the vertical polarizer, only the vertical component is going to go through. And the vertical polarized light does not have a horizontal component, so no light is going to go through. So which means that the sunglasses are polarizers. All right, the sunglasses are designed to reduce glare. The reason that happens, the glare happens, is because from certain surfaces like that, wet surfaces or water surfaces, at certain angles, only at certain angles, the reflected light is always only going to be horizontally polarized. All right, so the horizontally polarized reflected light is what you experience as glare, which in order to get rid of this glare, we have sunglasses, so sunglasses will be vertically polarized. So this is known as the Bruce angle. We'll study that formally. I think it's going to happen next week. So the reflected light at certain angles will be horizontally polarized, so that's known as glare. So the sunglasses are going to get rid of glare because they're vertically polarized. All right, so that's the reason. All right, so this tells us something about the nature of light. I want you to notice that the only sort of wave that you can polarize is transverse waves. Yeah, these wigglies are not the compression waves, but the transverse waves. So what do we know about the nature of light? It's a wave. It's a transverse wave. All right, so this is 19th century physics. These are the experiments. They kind of prove the fact that light is a wave. And then you move on to 20th century, all of a sudden the particles start to act like waves, and you go, waves of what? And if you're not looking, you get waves. If you're looking, you get particles, and everything's made up of particles. So how does an observation, an outside observer, collapse these waves into particles that create the universe? And then that becomes your modern physics, quantum theory. Everything is stranger than fiction. Universe becomes almost like a computer program or video game.
Almost.
Almost, but it's even more bizarre than that. All right, so pick and choose.
Transverse.
Transverse. All right, give yourself 5 points. So the debate is settled for now until modern physics. So those you guys have to take it. Obviously, you'll have to take it somewhere else.